other substances, and it just means there's the systems that we're observing, like the screen, is in some state which we perceive as so kind of the lowest it can possibly be, or the most basic it can possibly be, and we don't observe anything, any excitation above that ground state. So, speaking physically, and so that way we say, well, there's nothing. It's like, like for instance, well, we'll talk about that later. But if it's like the empty space from the point of view of particle physics, it's not really empty, and it just means all the creation and annihilation processes that are constantly happening are in some kind of steady mix. It's like you see this a steady mix of red, green, and blue, and so that connect. This is it's not white, but it's in the steady mix of these three colors we perceive as white. I mean, it's sometimes no color at all. And so question in the talk about, if a talk about, it's going to be, if somebody asks you tomorrow what was the talk about, you can say, well, the talk was about nothing, and so which will be true. But still, in the talk about nothing, you can learn something. And so what can we learn? We can learn that there's a definition to nothing. And once you give this definition, it has some properties. And then, in fact, sometimes you can even classify the nothings. Like, there's some, consider the moduli of nothings. And this it's not an abstract study. So somehow, if I, if you learn nothing, it can have applications. So, and we'll talk about concrete ones. And so informally, oh no, you see, that was supposed to be one sentence, and now you can have it. Yeah, but 2 copies of that, Oh, I apologize. Some next year I'll give a talk about the. We'll check Zoom ahead of time and then see if it works as expected. So the nothing has many names. So informally, you depending on your depending on what sort of how do you mathematically model a physical system. The idea that the system is in its most basic state has many different names, and people say it's in a particle physics. People would like to say maybe vacuum, because for them that's and then in the statistical physics community, people would like to say Gibbs state or some such thing. And so informally, that's a state of a physical system that refers to 2 infinities. First, it has to be in infinite space, means there's no influence of boundaries. That means, most physical systems we have, we hold them with their hands, or they sit in some container, and then they sit maybe on a desktop, on a tabletop. So anyway, there's some boundaries, and there's of course that those boundaries influence the system. And so first of all, you'd like it to be in infinite space, and also you'd like it to be an infinite exist in that state, and we're discussing be able to exist in infinite time. So it means whatever this is, if you think about try to apply it to kind of real life, that doesn't sound so attractive. Like the state, if you think what's going to happen with the humanity for an infinite time, it's not a very cheerful thought. So, but physically we can mathematically we can contemplate something existing. What's going to happen with the world when it exists for an infinite amount of time? Okay, well, we're going to be one. Will be one of the vacuum. And so this refers to this 2 infinities refers to, like I said, the spatial extent, and also there has to be some dynamics that has to whatever could happen will happen. And this you can see, there are many kind of physical instances that you can, observe something like this. Very popular, and we're going to talk about something like the Ising model, which is one maybe the most basic model of spatial randomness. If you have a field, field means a function. So some random function on the lattice that can take 2 values. Originally that was supposed to be magnetization, spin up or spin down, but you can whatever think of any kind of like something occupied or empty or some such thing, or this could be a state of a continuous media, well, air is a fine example. We have hard time picturing the air. So if you want to picture a medium, it may be easier to picture liquid, which is what you see here. And then of course, like I said, the particle physics, it's also, if you think about particles are constantly being created and annihilated, and this exchange interact each other by exchanging the force carriers and so on and so forth. There's some real mix there going on. And anyway, this is the general picture is that you have some degrees of freedom, which is in the Ising model case. I mean, again, this is some binary degree of freedom that takes at some point, maybe you could discretize your space. At some point in time, it takes a discrete value, plus minus one, say, and then or it could be many, much more complicated, with some degrees of freedom that defined in space, and they fluctuate both in space and time. And this sort of this people that is people call field, and studying this fluctuating fields called field theory, and it can be has two basic flavors. So this is in your physics department. There'll be people who study it statistically. It means they refer to properties of materials and so forth, that kind of random media randomness being statistical randomness, or do you have quantum? They're intimately connected, but I think it's easier for a mathematician to refer to probability. I think it's easier than talk about probability, since it's kind of intuitive. So there's some random stuff, and then it fluctuates, and so that's so we'll talk about that. And so oh no. Okay. It has this the print to PDF has a great batching average. It's like if never there's a formula, it splits the page right in the middle of the formula. Well, I hope you can somehow put the two halves together. So anyway, in statistical field theory, what's the state of the system? State of the system is described, first of all, an individual state of the system is described by the value of some function, which is some whatever could be, for example, let's stick to the Ising situation, or for example, you could picture like behind me, it's some function, some random real valued function taking values in the two-dimensional space. So it's some random so in the two-dimensional lattice, I take a random kind of height. So see if we plotted something like that, so that you see it behind me. So it's some function which can define on a space or defined on a lattice. Lattice is usually easier. And then so the function takes values in some whatever is the space where these fields take values. And so that's an individual configuration, but of course there's a very, very large set. And what the state of the system really is a measure on this. It says assigns probability to different events, like what would happen. Like if I ask what's the height of this column, what's the probability of this being between like 1 meter and 2 meters? That's an event which should have a probability, and so the measure on such events, it's the state of the system. Okay? And now, well, for instance, since I talked about the Ising model many times, so what's the Ising model? Let's take it in 2 dimensions. So in 2 dimensions, they have a 2-dimensional lattice. Here I took it I took a bounded domain, so it's not an infinite. It's not an infinite system yet. So here's just a finite grid, and on this grid I can have a function that takes values plus or minus 1. And so which I can visualize as I think of a spin up, spin down, or the corresponding cell being occupied or empty, or colored blue or white. Or so you can think of this as a model of many different things: model of magnetism, or model of maybe crystallization, being that some sites are occupied or not. And so and that means for example, this could be some kind of discrete model for like a interface between two phases of some matter. And so then, so this is the state. This is a state of the Ising model is some measure on configurations of this white and blue boxes, or oh, right, spins up, spin down. And so now what's dynamics? So dynamics is I don't know if it's a good explanation, but I studied in economics department, and I think it is a good explanation. But then of course I'm biased. So it's fun to explain. Of course, human life is described by the laws of that eventually go to the laws of physics, and so it's funny to describe the laws of physics by anthropomorphic analogies. However, we can relate to anthropomorphic analogies sometimes better than we can relate to the laws of physics. So let me make it. So energy is some universal physical quantity. So that's some some sort of, which can take whatever, any form. So anything is energy. You can create a particle, it costs energy. You want to create some kind of fluctuation or stress or whatever, that costs energy. So energy is like money. Okay. Well, I'm not saying money buys everything, so don't read me this way. But anyway, money is pretty universal. So so that's so then if you want to change the state of the system, like for example, you want to get a new, for example, you want to get a new piece of furniture, or go buy go buy something else, make some changes to where you live, or whatever. That's typically either this costs money, or they're actually gonna sometimes the energy, sometimes if you want to make a change, sometimes you lose energy, sometimes you gain energy. And so it depends, right? You can buy or sell. But uh, I'm not, I'm mathematician. I'm not saying that I want to say something profound about human life, but I think, okay, one can relate to that. And so then the rate at which you can make the changes, that should be somehow measured by whatever, how much money do these changes cost. And so then in economics, this is measured by the ease or hard, or how easy or hard it is to either borrow. Kind of, if you want to borrow money, means you want to borrow energy for something. What does it mean fluctuation? It has to borrow energy from, if you want to create something over the low energy state, then means you have to borrow energy from some other place. And so then it means that it's kind of like borrowing money. You go to a bank, you borrow money, or you in your phone app you borrow, somehow, anyway, however that means. And so this means that there's some quantity which is like the interest rate, which tells you how easy it is to borrow, or what is, so to speak, what's the how easy it is to for a system to borrow energy, or how the system likes to. And of course, if there's a quantity, it's called inverse temperature. It's actually the definition of temperature in physics. It says that's how it measures. It's like the interest rate for the energy. Meaning, so now I come to this meaning, that if you have some fluctuation and there's a change of energy, then the probability of that fluctuation happen, suppose you have some fluctuation, that should be exponential with the change of energy. So it means if you have to gain, if it costs energy, then exponentially hard. This is exponentially hard to the more energy requires, the probability of that event decays exponentially. But the rate at which decays exponentially, this is to say you have an exponential dimensional quantity. So you can't take an exponential dimensional quantity, it has to be measured in something. The rate at which you take this exponential, that's called temperature, or rather the inverse temperature. So in other words, temperature is something which is measured in the units of energy, and it tells you the probability of any change. This exponential decay with energy, you have to divide by the temperature. So that's the definition. What it means to fluctuate at. So this means what it means to fluctuate being in the context. So it means you're in the context with some outside, some ambient world from which you can to which you can emit energy or gain energy from the outside world, and the ease of that process, it's called the temperature. So that tells you how much the outside medium likes you to can give you energy that for you to fluctuate. Okay. So now concretely for the Ising model, the energy is defined to be the following: the like spins like each other, and opposite spins dislike each other. So it means if I take sum over all neighbors, and I take just the product of the values of the spin at the nearby sides, then I get, well, if they're aligned, I get 1. If they're disaligned, I get -1. And so if I take the minus sign of that, that will be saying the lower energy state is when everybody is aligned, and the higher energy state is where, whatever, that's when they're not aligned. And this is, of course, this is the same up to some constants. This is the same as the length of the interface between, so if you think about it, if you length of the interface, so here is between the blue and the red is the interface. So between the blue and the white is the interface, which I've drawn in red. The length of that interface is the energy, which makes sense. If you have some interface between two phases, then there's some energy associated with the interface. That is, how would you how would you measure the energy of the interface other than its length? That makes sense, right? And so then the Gibbs states now are the states which are invariant under updates. So it means you have some measure that if I take, updated, that means, what does it mean, the updated? It means I take any part of that. I mean, I have my system. I fix any finite part of that, like in this picture. In this picture here, I take any finite part of this picture. I flip the spins in it any way I like, according to this law. Means according to the probability is so the change of energy is some finite function. So any flip in the finite side will be some finite function, and I do that, and I get a new measure. But that measure has to be the same as before. Right? So that makes sense. And so then you can ask, well, it's like, so this measures invariant under this process. They're called the Gibbs state. And strictly speaking, measures, well, we'll talk about it in a second. Before I'll talk about it in a second, then of course this is named after Willard Gibbs. Boltzmann and Gibbs were the people who are first thought about how the rules of ordinary mechanics should modify to give us kind of a meaningful like a modern way of thinking about well, they would say thermodynamic quantities, but really statistical physics. I mean, they would say, and the given definition, this goes back to Dobrushin, another really remarkable mathematician. And so maybe to go over this definition one more time, you have a set of all possible measures. So that's, if it's some space, in fact, some topological space, the topology being defined on usual topology on the space of functions, for example. And then inside, so you take all measures there. Then there are some measures that are invariant under this update. These measures will form on abstract grounds. Since this abstract ground, this will be a compact convex set. Just because this is by some kind of Tikhonov's theorem, or somebody's theorem. Sorry, I'm not. I apologize if I'm showing. I think if I had to pass an abstract measure theory exam right this minute, I would probably, my grade would be not so great, I'm sure. But anyway, this is since I haven't taught it in a while too, so it's anyway. So this is by classical theories of the subject as a convex compact set, and then we want to only look. It's interesting to look at extreme points of that set. So suppose because what does it mean? You have some one measure and another measure. Of course, you can mix them. So, for example, if you have the famous Schrödinger cat or whatever, it can be kind of in one state with one probability, in another state another probability. Then we don't want that. Means we don't. One can take it, but it's not interesting. So we'll take, if out of all invariant measure, we'll just take extreme ones. Means the extreme points of this compact convex set. This is people all say this is ergodic. So under this procedure, you take the ergodic invariant measure. Means ergodic means they're not convex combination of something else. And so these are called, so this, imagine if your set of imagine if your set of measures like a segment, and then you just take the endpoint. So this is my picture illustrates this here. And for Ising model, indeed, that is the case. So for Ising model, there's a parameter temperature, and it's a pretty, it's a classical theorem in the subject, that the set of this Gibbs measure looks as either a point or a segment, and so that means the extreme ones are either 2 points or 1 point, depending on the temperature. And it's, if the temperature is, there's a certain critical temperature where this transition happens, and below that temperature you have two different Gibbs measures, and they're characterized by having a prevalence of either blue boxes or the white boxes. And then at the critical temperature and above, you have 1. And so this is a picture here to illustrate the typical configuration. So if you're above the critical temperature, just basically you see more or less a random collection of, here it's black and white since it's taken from an old paper when they didn't print on color yet, and they shouldn't print on color. And anyway, they should just put color pictures online. But anyway, this is so above the critical temperature, you get a pretty even mix of, kind of random mix of white and black. At below the critical temperature, it's either majority of one spin, so it means you have magnetization. And at the critical temperature, you have this really interesting fluctuation. You have big kind of means you have islands within islands within islands. So it's a self-similar type of situation. It's very nice. And you can measure this. So for example, what is the function? So how would you picture the set of measures? Well, what are the functions on the set of measures? Well, it's easy. So if you have a set of measures, and the functions on that are integrals of anything you want against that measure. Like for example, you can ask, so if I have a random configuration of fields, and I can ask what's the expected value of the spin at, say, the origin. So I have a random spins pointing, having values plus or minus 1, and I take the one at the origin, and I could have taken any other place. And I take that, so it's sigma of 0 is the value of this plus minus 1 in the origin. I take its expected value, and that expected value is function of temperature. It's going to look like that. I've plotted it here, but it's not. It's plotted here by hand. It's not a real plot, but it looks this way. So it means if it's below critical temperature, then it will then in one of them it will start out being, say, exactly 1 or exactly minus 1, and then it will this is called magnetization, and then that magnetization will go to 0 with interesting power law, and it'll stay at 0 after that. So this is really picture of that set. What you see here is really plot of that set with its natural structure of, like, whatever, real analytic something manifold with singularity or something like that. So, and so in general, you can ask, if that, what are the coordinates on that set? The coordinates on that set, well, again, these are all possible things you can measure. Like, for example, if you talk about a gas, then you can, what are the things you can measure? You can measure, say, the density, which is the expected, which means the expected number of particles in some volume. You can measure the temperature, which is the expected number. So the temperature here will be, okay, this will be, you can what it means to measure temperature, it's roughly temperature tells you the energy density. So this means here it will be for an ideal gas, this will be, say, this will take the expected kinetic energy of the motions of these particles with measured in some per volume. And then you can also measure pressure, which means momentum. You put some say you have that lid, and you measure the momentum you get from particle hitting that lid. And so, in principle, you can measure more and more things. Like in Ising, you can measure more and more things. But it will turn out they're all functions of, in Ising, of one variable, namely the temperature. And for ideal gas, they're all functions of 2 variables. So if I name you 3, means you have the temperature, pressure, and the density, and they connected. Already these 3 satisfy equation, namely the equation of state. So the famous equation of state written here, and so that means the space. While for the Ising, the space of this Gibbs measure was this one-dimensional look like that, and so the space for the ideal gas, the space of this Gibbs state is two-dimensional, and this, if you plot it in a three-space, that will be plot. The plot would be this equation of state. Three-space being both three coordinates I just discussed. And so this is I want to talk a little bit about the case when we're at zero temperature, because this is, so you can ask, well, Ising is some kind of model of magnetism and could be taken in any dimension, and then you can ask, what about three dimensions? Okay, there's a amazing numerical progress recently on three-dimensional Ising, which it's not the topic of this talk at all, but if you want some sort of analytic understanding of three-dimensional Ising, that's far away. But at zero temperature, this is what let's talk about that. But in general, what does it mean to have at zero temperature? Means anything which is not, any configuration which is not strictly minimizes the energy, that's just prohibited, because zero temperature means if you have to borrow 1 cent of energy, or whatever, one millionth of 1 cent of energy, that already costs you infinite amount of probability. You lose, you really have to sit at configurations really minimal energy. And so this is what does it mean to what does it mean for an interface like I'm showing here? What does it mean for an interface like this to have a minimal energy? Means it has to be like a minimal surface in the sense of these discrete surfaces. This is sometimes people call it like whatever Manhattan metric, means a minimal length. A geodesic in this Manhattan metric is not a straight line. It's something there. First of all, there are many of them. So if you have to cross whatever 5 avenues and 7 streets, then there'll be 12 choose 5 ways to do it in a minimal way. You just means you every time you just go, whatever, whether you go the way you, every time you get, at every corner you get a choice, until you get to the point you want. So this is, and so the analog of this in 3 dimensions is you imagine, so this kind of stepped surface in 3 dimension, what does it look like? It's going to be instead of a picture of making a turn at every corner. Now you have 3 kinds of steps, and you can arrange them. So everybody picture this being a projection of some 3-dimensional surface which have 3 different kinds of steps. So you think of a sides of a unit cube, and then the sides of a unit cube, these are like 3 elementary steps, and you can combine them in a way that minimizes this discrete surface area in many different ways. But you can also take this view this model as a purely planar thing. So it means you can think of this as instead of a surface in 3D, you can think of this as just tiling of a plane by 3 kinds of rhombi. You can also identify with the dimer, means because you think of what's a rhombus. If you take the underlying, if you superimpose this your rhombi tiling with this hexagonal lattice, you see that each rhombus covers 2 vertices of this lattice. So it's like saying I have some planar lattice, and I assigned for every neighbor another neighbor. So I matched all vertices of my graph in pairs. That's sometimes called perfect matching, sometimes called fully packed dimer. Anyway, so it's also familiar. And so what's a Gibbs state? A Gibbs state, now we decide that this is so the Gibbs state is, again, you take a part of this picture, you fluctuate it, means you fix it outside of some fixed region, and you're allowed to fill it in any way you like it arbitrarily. Now the energy has to always be minimal. And what does it mean minimal? It means you feel it in the surface with no overhang. I mean, in 3 dimensions, you feel it with the surface with no overhang, and in here in the plane means you feel it, well, you feel it according in all possible ways, but they all from the point of view of surface separating two phases in 3 space, they'll be all minimal. They'll have all minimal energy. So that makes sense. So this is the Gibbs, I guess. So with Gibbs states are the measures. So we're taking measures on tilings of the whole plane by 3 kinds of rhombi, and the condition on the measure is that once I fix it outside a compact region, and I resample what happens in that region in any way I like, that measure stays invariant. And what we observe is that this object has a conservation law, namely the number of tiles. If I resample, then I always have to choose the same amount of tiles of 3 given colors. And maybe it's easier to convince yourself of a different statement, is that namely I can always go from any 2 ways to fill in this picture. I can connect by flipping one single, if I take one single cube and I flip it, then I can go from any to any. And of course, if I flip a cube, I had 3 different 3 different tiles, and I still have 3 different tiles after I flip. And so this means the density of 3 kinds of tiles, this is some conserved quantity. If I had a certain density, then after resample, I have the same density. Right? So means the space of my Gibbs state that maps to a triangle. So that 3 different kinds of tiles. There are 3 different densities that have to add up to 1. So this is space of state as a triangle. So with coordinates, with the probability to see the tile of a given shape. And so then the space of Gibbs state maps there, because for every Gibbs state there's a certain density of tiles. And it's been for the longest time people were trying to prove that that's in fact more or less isomorphism, namely isomorphism over an open part, because at the boundary some funny thing happens. At the boundary, the definition I gave is not a good definition. But it's been a conjecture for the longest time, and very smart people thought about this and somehow. Well, so this is, but it's been recently proven by a very bright young fellow named Amol Agarwal that in fact this space, this is an isomorphism over the interior of this triangle. That's an isomorphism. Means for every density of tile there is a unique Gibbs state, and in particular it's translation invariant, because I have a Gibbs, right? I forgot to say the space of all possible vacua, that is translation invariant, and this is translation act. If I had some vacuum and it translated in space, it's still a vacuum. But it's not clear at all that all of actual measure have to be translation invariant. But that in this particular is true. And for the translation invariant measures, those were understood. Those the actual what this measure really are. So Amol's theorem amounts not so much to finding them. All of this, the translation invariants were known before. People understood them really well. But the proof that there is nothing else, that's the content of the theorem. And in the translation invariant measure, they have extremely nice, because if you ask for probability of any event, it's some nice determinants. And I invite you all to read, well, there are many expositions, but the one by Rick Kenyon is, I think, particularly nice. Actually, you should all read it. I mean, not whatever, whoever is interested in that sort of thing, I invite to read Rick Kenyon's lecture. And so that's to summarize, people knew the translation invariant Gibbs measure. They have a very nice description, very nice formulas for all events, and so on and so forth. but the fact that there's nothing else, that was a really hard theorem that Amol proved. And it's kind of a pretty amazing result in mathematics, if you ask me. So to summarize, so again, so the summary, I have a page break right through the middle of my summary. So the space of this vacuum, the space of Gibbs state, may be non-trivial and may be very interesting, and maybe at least hard to accept or access, or at least hard to prove. There's nothing else. Another topic, is that would that be acceptable since it's I know it's not your fault that the Zoom was malfunctioning. Yeah, maybe would that be acceptable if I talk a little about just a tiny bit, maybe for 5-10 more minutes on something which is related. So so it's interesting to study not just vacuum, but also think about kind of like a map from your domain to the space of vacuum. The way to think about it is think about like modulated vacuum. I mean, something which is and so maybe I explained it by analogy. My favorite analogy is like the weather map. So if I have a weather map that will have, this means, so your space is the surface of the Earth, or you can think of three-dimensional too. But let's say take the surface of the Earth, like the surface, weather of the surface. Then people will plot the pressure and the temperature. Like here's a temperature plot of the southern hemisphere. So this is what does it mean? It means you have some state which is on a scale of on a human scale. We have the air is pretty much in an equilibrium, so there's a certain we're in some Gibbs state on a human scale. So at the point we can kind of measure the parameters of that equilibrium, means the pressure and the temperature. But then, of course, that varies over time. So the temperature is not a constant function. It's if you go a certain distance, that will change, right? So this is like a modulated vacuum. You're in a vacuum, but its parameters of that vacuum change very slowly. So there's some hierarchy of scales. There's a scale of the actual molecule of nitrogen. And then there's a scale of us, and then there's a scale of the Earth. And so we are much higher, much larger than molecules. And so whatever happens with the molecules equilibrates at the scale where we are. But then what happens at the scale where we are will change slowly at the scale of the physical system. And so this is and you can picture this. Suppose I have now this stepped surface. Suppose instead of taking it infinite, I take it very large, like I want to span a given contour. Then so this will mean that I can, if it's a very large surface, that will have a certain, at every point it will have at every point of this picture, I can see a certain density of tiles forming. And so from this picture there will be a map to my triangle. And so if this picture is very large, then at every point I imagine will be some density of tiles. And so at every point I have a map from my space to the space of steady state, to the space of vacuum, to the space of Gibbs measure. This is like plotting temperature. It's exactly like plotting temperature on Earth. And what's remarkable is that in this picture there will be, in pictures like this, there will be a certain law of large numbers. We can describe what it happens. It's because, well, let's choose some scale, which is like we discussed before. It's intermediate between the scale of the box and the scale of the whole picture. And then ask ourselves what's the probability to see something. First of all, so what's the probability to see something on that? So that we choose the right box. And something, like I said, this is like our scale compared to the Earth and the molecule. So this on this on this scale of this rate frame, we see some vacuum. I mean, this is infinite, and I mean, this is from the point of view of box, it's an infinite thing, and so there's like some vacuum. So in each one of these red frames, we'll be in some vacuum, and then but then there's different red frames. If you look at the that frame is one part of the picture, red frame is the other part of the picture. They're very far away because the picture is much larger than us. And so then, so they will be independent. It's easy to imagine. And so you can ask, what's the probability to see any particular configuration? What's it going to be? The probability of independent event is going to multiply. So if I take the log of probability, so I forgot the log here. If I had I were rewriting that, I would add the log, but you should imagine that from the probability stands log. And so then, so the log of probability will. So what was previously probability was multiplicative, now it's going to be additive. So this would be some sum over all these red patches, and then you have to take the logarithm of number of states in this red patch divided by its volume, and multiply by the volume again, which means you integrate with respect to the volume of function, which just tells you what's the logarithm of the number of states per unit area. This function has many names. It's called entropy and so on and so forth. Since we're here, that it's also related to free energy, but here we're at zero temperature, so entropy and free energy is the same. And so this is, in general, their function like this on this space of Gibbs measure. There's a very important function like this, like free energy. So it's very important. It's a very important function. And what it says that by solving a certain variational problem with this function, you find out what happens in systems not of infinite size, but of finite large size. If you have a system of finite very large size, this will not be in a may not be in a pure vacuum state, maybe in a modulated vacuum state, but in which state it's going to be, this will be solving some variational problem involving this very interesting function on your. So you have, in my case, I have a triangle. There's a very interesting function on the triangle. And okay, so this is again, there's in this particular instance, there's very nice formulas for this function and for the solution of the variational problem too, because here, I mean, you see this, if you look at this picture, you see the cardioid in this picture just staring at you. So this must be something happening. I mean, it's an inscribed cardioid inside this polygon. So there must be something happening with the solution of a variational problem. And in fact, here it's the case that this sort of thing you can analyze really push through to exact formulas. And maybe one place to read about it is I don't think Rick's lectures contain so much about it, but I mean, okay, this is another thing. Once you finished with Rick's lectures, maybe you can look at my notes called "The Limit Shapes Are Real and Imagined," and it can be found on my website. It's yeah. But one application which I'd like to mention is that this sort of thing. So since I said have applications. And what are the applications? Like, for instance, you have a very, very large system, and you'd like to know what does this large system do on a microscopic scale. Seems okay, well, it's a very, very hard problem. So, so meaning here I have this random surface, large, spanning some contour, and then I take a magnifying glass and I look what happens at some particular place. But now we know how to solve this problem, because what's it going to be? First of all, we know by variational problem, we know in which vacuum state is it going to be at this local scale, at this local plate, because first if some variational problem tells you what would be the distribution of the vacuum over your space. So it says in which vacuum you're going to sit at this given point. And then in that given vacuum, if you have, so since we have a classification, we know exact formulas for the probability of any given event. Like if we would like to know what's the probability that have two rhombi somehow positioned any way we like, for this there's a formula. So it means, so in the end the result is that you take the formulas for these Gibbs measures and they depend on parameters. You stick parameters that you get from solving a variational problem. That's the answer. That's pretty amazing, right? I think it's it's a little bit like a settled point integration, but it's of course happens in some kind of really infinite dimensional space. But it's so it means there's some abstract expression depends on some parameters, and the parameters itself, like the position, it's like find the parameters from solving some variational problem, which is pretty cool. And so now I hope I convinced you that there's really countless problems of the kind that if for some physical system describe all possible Gibbs states or modular spaces of vacua. And we had this example when the conservation law leads to the more conservation laws you have, the bigger that space. And this here you can count not just ordinary conservation law, but also supersymmetric conservation laws. They also contribute to the richness. So if you have some system, not with this all symmetries, but also with supersymmetries, those will contribute to the richness of your moduli space. And then once you done with the space, so in this, in our example, the space was either we had 2 points, we had a triangle, we had plane. So anyway, some space, and it has an interesting function on it. And then you would like to know what's this entropy function? What is the variational problem? So that's another thing that's not easy to know, but in many cases you can. So it means for every such x, there's some variational problem. And ideally, you would like to know what this problem is or what its solutions are. And again, the more symmetry you have in the picture, the better. So for instance, supersymmetry really helps here. And the fact that and then and once you're done with that, so it's like in math, it can go on and on and on. So it means you've usually there's some very hard problems even to find the Gibbs states, but if you solve that problem, you can ask more questions and so on and so forth. And so once you're done, if you understand the solution, if you understand the variational problem, and then you can ask about the solution. If you understand the solution to the variational problem, you can ask, well, how about I study the solution? Means solutions are not going to be it's going to be some other set. So solution to the variational problem is some interesting other set which you can study, and study to how it depends, how it depends on the boundary condition, other parameters. Some interesting. It's right. I mean, if I have a surface, if I run a surface spanning a given frame, I can say, well, what's going to happen if I change the frame, or what's going to happen if I do this or that. So that's something really kind of really worth studying. Now I'm over time and I'm at the end of my slide, so maybe we'll I thank you for your attention. I'll eager to hear your questions. Let me check if that I'm at the end of the slide. Yeah.
Okay, thank you very much, Professor Okounkov. So yes, we are a bit over time, but I think we have time for a couple of questions or comments. I don't know. You can either write in the chat, or you can unmute yourselves and ask the question directly.
Hi. Thanks for that. I'd like to ask. I was a bit confused about. So on about slide 3 or something, you were describing the vacua, and you said, you're talking about the set of all measures on your system, and then inside that set of all measures, you have these measures that are invariant under updates, and that somehow forms a convex compact set, and then the extreme points of that set were the Gibbs measures, I think.
Yeah, usually you call that Gibbs measures.
Which one is X? So which one is X? Is the space of vacua like the space of measures invariant under updates, or is it the extreme points of that space?
Usually the extreme points, yeah. So here, this is so like in this example with the stepped surfaces, we're talking X is a triangle. I mean, essentially a triangle. There's some stuff at the boundary, but essentially a triangle. And for each triangle, there's unique indecomposable Gibbs measure with that slope. If you'd like, so it means you have the set of all possible invariant measure is is a set of which the extreme point already form a triangle. So it's a very, very infinite-dimensional space, but its extreme points are two-dimensional.
So which precise system was that? Was that the three-dimensional Ising model, or which?
Yeah, well, this is the step surface. These are the step. These are the interfaces in 3D Ising at 0 temperature. So this is step surfaces. So maybe we'll go here. So
okay.
Here. So this is. So if I give you the density of 3 kinds of tiles, there's unique indecomposable measure with these densities. But then if I'd like, of course, if I give you any measure on the triangle, then if you can mix those and get another measure. So the set of all invariant measures like all measures on the triangle, but the extreme points are just points on the triangle, the delta measures on the triangle.
Thank you.
Sure.
Okay, I don't know if there are any other questions. Okay, so
well, then I want to then maybe thank you again for the invitation. In the chat. Okay. Oh yeah, so the numerical is so that's about this bootstrap program. That's a big program in theoretical mathematical physics. Is that you'd like to be able to solve just from the kind of self-consistency of in this case statistical field theory, you get some equations on what would be like, for example, the analog in 2 dimensions. Thanks to conformal field theory, we know exactly what would be. So maybe let's go here. Where was that picture? Here. So in 2 dimensions, first we know exact value for the square grid. We know exact value of the critical temperature, but okay, maybe it's not such an important number. But we also know the exact power law by which magnetization goes to 0 at the critical temperature. But this is mathematical now. Now in 3 dimensions, there's no mathematical theory that tells you this. The power law is called the critical exponent. There's no mathematical theory that tells you what this critical exponent should be, but there are equations which very complicated equations, because in principle it's an infinite set of equations, but you can solve them numerically, and means there's some approximation scheme which you can run. People are able to run it, and people are able to compute these numbers with very high precision, matching the numerical experiments and so on and so forth. It's pretty amazing, yeah. But and this is from all of that from just consistency, from kind of internal consistency of the theory. We give you some sets of equations. Like I said, mathematical very hard to study because it's an infinite set. But numerically, you can make approximation and you can get good results.
Okay, so thank you.
Yeah.
So I think.
Well, thank you. I apologize for this, for the curveball, the Zoom curveball at the beginning. I hope, also, so this is. I hope you were able to, somehow. I hope the fact that I have to show you the slides the way they are, didn't somehow.
No.
Well, anyway, it was so. Next time we'll do a more thorough test of the capabilities ahead of time. But, yeah.
Okay. Well, anyway, we enjoyed it. I enjoyed that. I'm pretty sure all the other participants as well. So I think we can also express our thank you to Professor Okounkov. Maybe you can unmute ourselves and clap for him. Okay. Thank you.
Oh, super. Thank you.